Welcome to The Explainer. Today, we are taking a seriously fascinating journey together. We're going to look closely at one of the absolute most powerful, yet honestly kind of misunderstood, energy sources on our entire planet. We're tracking the unbelievable trip of power, starting from a single, microscopic atom all the way to the massive electrical grid that lights up entire cities. It's a total marvel of engineering and physics, and we're going to break the whole shebang down step by step so the entire process is completely clear.
Okay, let's dive into this. We all know nuclear power plants exist, right? And we know they pump out a massive amount of reliable electricity around the clock. But how do they actually do it? I mean, really think about it. What is the actual mechanism that turns a chunk of mined metal into the power that runs your television, your fridge, your lights? That is the core question we're answering today, and honestly, the answer is surprisingly elegant.
Quick thing before we literally crack open that atom. If you love clear, simple breakdowns of complex topics just like this one, go ahead and hit that subscribe button right now. Join our community. We're all about stripping away the confusion and getting straight to the core of how the world really works. We focus on clear, visual explainers that totally respect your time and your curiosity.
So let's start with the microscopic spark that kicks this whole process off, nuclear fission. In the absolute simplest terms, this is a physical process where the atoms of a specific type of uranium get split apart. Imagine a tiny little particle, called a neutron, slamming into a uranium atom. When that incredibly precise collision happens, the atom splits. The strong physical bonds holding it together just literally break apart. And breaking those bonds releases a truly massive amount of energy in the form of heat. But wait, it gets better. When that atom splits, it releases even more neutrons, which then fly off to collide with other atoms, creating this continuous self-sustaining chain reaction. And it's that steady, unrelenting release of intense heat that serves as the fundamental engine of the entire plant.
But how does this microscopic concept become something physical we can actually use? Because you can't exactly just toss a pile of raw uranium into a room and hope for the best, right? The uranium is carefully, meticulously processed into these small ceramic pellets. Those tiny pellets are then stacked end-to-end inside long sealed metal tubes, which we call fuel rods. Finally, hundreds of these long rods are bundled securely together to form a single fuel assembly. This highly structured, precise packaging is exactly what allows the engineers to safely handle, arrange, and control the raw fuel inside the heart of the power plant.
And that heart, that's called the reactor core. So the absolute crucial point here is understanding the environment inside this heavily protected core. Because these bundled fuel assemblies don't just sit out in the open air. No, they are completely submerged in a continuous bath of water. Now, this water does two vital jobs. First, it acts as a moderator. It actually slows down those tiny flying neutrons we just talked about, which is strictly necessary to keep that chain reaction going smoothly. Second, the water acts as a coolant. It absorbs that intense, continuous heat radiating off the splitting atoms. And to keep the whole thing perfectly balanced, operators use what are known as control rods. They can slide these strong neutron-absorbing rods deep into the core to safely slow the reaction down, or pull them out to naturally speed it up.
To really picture what's going on inside that massive steel container, the Nuclear Regulatory Commission uses a really brilliant description. They describe the reactor vessel as, quote, somewhat like a gigantic pressure cooker. Because the heat generated by the nuclear fuel is so overwhelmingly intense, if the water were just sitting in an open pot, it would instantly boil away into absolutely nothing. But by keeping the water under immense crushing pressure inside this giant sealed steel vessel, the water can soak up an incredible amount of thermal energy without ever actually boiling into steam.
Now, how we actually get the steam needed to generate power brings us to the two main types of light water reactors, and this brilliantly illustrates the clever engineering at play. First up, we have the pressurized water reactor, or PWR. In a PWR, that super hot, highly pressurized water from the reactor core never actually boils. Instead, it flows through a primary loop and transfers its heat to a completely separate secondary water system. It's that secondary system that ultimately boils and creates the steam. On the flip side, we have the boiling water reactor, or BWR. This one's noticeably simpler. There's no secondary loop here. The water is just allowed to boil directly into steam right there inside the main reactor core. Regardless of whether it's a PWR or BWR, we now have highly energetic steam. So what do we actually do with it? Well, we send it over to a machine called a turbine, which acts exactly like a highly sophisticated giant windmill. See, when water turns to steam, it expands rapidly, demanding way more physical space. So this steam travels at incredibly high speeds out of the boiler and violently pushes against the blades of a massive turbine. This is literally the absolute crucial moment of transformation in the plant. We're converting the thermal energy of that intensely hot steam right into the spinning, kinetic, mechanical energy of the turbine shaft.
Okay, so we've got a powerfully spinning shaft. But how does a spinning piece of metal become the electricity that charges your phone? To really grasp this, let's think about a standard electric motor, like the one in a basic household fan. In a motor, you apply electricity, and electromagnets inside push and pull on each other to make a rotor spin. Well, an electric generator is simply a motor in reverse. Instead of using electricity to create spinning, we use the spinning from our giant steam windmill to create electricity. As the turbine forcefully spins the rotor inside the generator, magnets push and pull against each other, and that right there is the exact moment physical, mechanical energy is converted directly into electrical energy. So once the steam has done its heavy lifting job of spinning the turbine, it needs to be cooled back down into liquid water so it can be pumped back into the heater, continuing the cycle all over again. To see how that happens, we need to step outside the facility. And that brings us to these iconic, monumental structures. These are natural draft cooling towers. Their immense, towering scale against the landscape is truly breathtaking, and their specific shape, which is called a hyperboloid, is actually a highly intentional feat of engineering. The broad base provides a massive surface area for evaporation. The structure naturally narrows in the middle to rapidly increase the velocity of the air flowing up, and then it widens at the very top to smoothly mix the moisture right back into the atmosphere.
Now, what's really interesting about this slide is that when you see that famous, distinct cloud leaving the very top of these massive towers, it actually reveals a huge misconception. It's widely misunderstood that this is harmful pollution. Let's clear this up. It is not smoke billowing into the sky. It is simply entirely clean water vapor. It's just the natural result of cooling the steam from the turbine back into liquid water. And here's the absolute most important takeaway fact for sure. This is a completely closed system. The water circulating inside the cooling tower never ever comes into contact with the radioactive water circulating inside the nuclear reactor.
And that brings us to the final step of our long journey. From the incredibly complex microscopic splitting of a single invisible uranium atom to the massive monumental engineering of the giant steam turbines and generators, it all culminates right here. The electricity effortlessly flows out of the generator, steps up in voltage, and travels across these high-voltage power lines. This continuous, incredibly reliable flow of clean power pushes out into the vast electrical grid completely seamlessly, ready to silently light up millions of homes, schools, and businesses around the clock.
It truly is a breathtaking marvel of modern engineering and applied natural physics, which leaves us with a truly provocative thought to ponder. With the incredible ability to produce vast amounts of reliable energy and doing so with absolutely zero carbon emissions released into the atmosphere, is this incredible process the ultimate key to our clean energy future? It's a fascinating question, and I really hope today's explainer gave you the solid, simple foundation you need to understand it. Thank you so much for taking this journey with me today. Please don't forget to hit that subscribe button for more clear, structured explainers, and I will see you in the very next one.